Hello, welcome back. The name of this section is called Completing the Square. This is part 1. This section is actually so incredibly important that we're going to have not 1, not 2, not 3, not 4, but 5 parts to this lesson. In this lesson, we're going to learn about what completing the square is. We're going to go through a couple of examples to make sure you absolutely understand how to do it. But then in the next several lessons, the next 4, we're just going to increase the problem complexity, making them harder and harder and harder to actually use the technique. But we'll be doing exactly the same steps that we've actually going to learn in this lesson. So we know that quadratic equations are one of the most common types of equations we solve in real science and math. We know that we really want to solve those types of equations. We've learned how to solve some quadratic equations in the past. We've learned specifically how to factor them and solve them by factoring. And we've learned the very special ones. We called them perfect square quadratics in the last lesson, where we could just basically take the square root of both sides. What we're going to do here is learn how to solve any quadratic that I give you. I can give you literally any quadratic I can think of, and you will be able to complete the square in order to solve it. And this concept of completing the square is going to tie directly into the next topic we're going to talk about, which is the very famous quadratic formula. I'm just going to give you a little bit of a punchline. The quadratic formula comes from this concept, the completing the square. In other words, I'm going to derive the quadratic formula and show you where the quadratic formula comes from in the next lesson, in the next topic, from using the concept of completing the square. So that is how important it is. It actually is used to derive the quadratic formula, which is one of the most famous formulas in all of algebra. So let's crawl before we walk. We want to talk about what we're doing and what we know from the past and what this is and how it ties into where we're going in the future. So we know that we can solve by factoring. So some of these things we can solve by factoring, right? And, we've done this many, many times, so much so that you might not even realize that it was a solution technique. But for instance, if I gave you this equation, which we've done this before, all this stuff is stuff we've done, x squared plus 2x plus 1. Now this is a quadratic equation. You know that because it's an x squared, and we're setting this equal to 0. So what we're doing is, if you were to plot this quadratic equation, it would have some crossing points on the x-axis. It turns out that there might not be crossing points there, in which case you'd have imaginary solutions. But if we did have 2 crossing points, those would be the real roots of this equation. And if it was hovering above the axis or below, then we would have the imaginary solutions because there would be no crossing points at all, right? But the way that we learned how to solve this in the past was to first try to factor it. So we draw the 2 binomials and set it equal to 0. And we say, well, we have an x here and an x here to multiply, giving me x squared. Only way I can get a 1 is 1 times 1. So the only way this is going to really work out is with a plus sign and a plus sign, right? So we've learned how to do this before because you can multiply it out. This is going to give you 2x. This is going to give you, 1x. This is going to give you 1x. You add them together to get 2x. The last terms multiply to give you 1. The first terms multiply to give you the x squared. So this is the factorable form, and you learn that to solve this guy, you just say x plus 1. You can set this term equal to 0, and then, of course, it's identical, but you can say that this other term here is equal to 0. So then you could say x is negative 1, x is negative 1, like this. All right? Now, what does that physically mean? It's a double root, right? We have 2 roots, but they're exactly the same thing. And we learned about that in the past. Let me just go over and kind of draw on a side here. If we were to draw this thing, we're saying that this thing has roots at negative 1. Negative 1 is somewhere here. And that means that the graph of this thing, if you were to draw it, would go down and then touch and then go up, something like this. So I'd have a double root right at this point, right? But the point is that we learn how to solve this by factoring. So the very first thing you do when you see a quadratic is you try to factor it. But as you know, you can't factor some of these things. So you can't do this unless you know how to factor it. So let's give an example of when you don't know what to do because you don't know how to factor it. For instance, if you can't factor something, can't factor the following equation. What if I give you x squared plus 2x plus 9? So this is exactly the same form as this one. And of course, we're setting it equal to 0. And we would like to solve it. The first thing you do is you try to factor it. So you put your parentheses here. You set it equal to 0. The x squared is exactly the same. And then you have to ask yourself, what times what is 9? So the only choices I really have is 3 times 3. If I put a 3 here and a 3 here, then I'm going to have a 3x and a 3x. That's going to give me a 6x, so that's not right. And then if I change this around, instead of 3 times 3 and make it 1 times 9, which will also give me 9, it'll be 1x and 9x, which which there's no way you can get a 2. Even if you change the signs, it's not going to work. So you cannot factor this. Now, this does not mean that this has no solution. It just means that you can't solve it by factoring because there's no way to factor it with whole numbers like this. With whole integral numbers, there's no way to get it all to work out so that you can factor and then set everything equal to 0. So do you give up? No. What we're going to learn is a technique where I can solve this equation, no problem, but I just can't do it by factoring because I don't know how to factor it. So keep this in the back of your mind. Let's go over here and talk about the following thing. Let me draw a little divider bar here. And let me remind you, in the last few lessons, we've learned how to solve these things. We can solve what we called perfect square quadratics. These were called perfect squared quadratics. And what did they look like? Let's give a couple of quick examples. The perfect squared quadratics with 2x minus 3 quantity squared is equal to 7. And another example would be something like x plus 5 quantity squared is equal to negative 4. We know how to solve both of these things. These are called perfect squared quadratics. We just did it in the last lesson. How do we solve them? Well, we have the variable tied up on one side with a square. So we take a square root of both sides. That reveals the variable and allows us to manipulate and solve. We take the square root of both sides here. But the problem is we have a negative 4. So when we take the square root of that side, we're going to get an imaginary number. We'll get 2i. So when we solve this one by taking the square root, we're going to get imaginary results. When we take the square root of this side, of this guy and solve, we're going to get real answers. But the point is we know how to solve both of them, but the only reason that we can solve it is because this thing is in a form so that I can just take the square root and neatly cancel everything related to this variable. I can't take the square root of both sides of this because the variable is in 2 locations. But I can do it here because it's nice and wrapped up like this. So what we're going to learn about in this lesson is called completing the square. And it just is a technique that lets us start from an equation like this, which we cannot factor, and we cannot take the square root of both sides, we cannot solve, and we're going to change it so that it looks like a perfect square quadratic, which we do know how to solve. I'm going to say that 2 more times because it's so important. When I first learned completing the square, I didn't understand why we were learning it. The reason you're learning completing the square is because up until now in algebra, you only know how to solve very special quadratic equations. You can only solve them if they're factorable like this. And you can only solve them if they're very, very easily able to take the square root of both sides like this. But you do not know up until this point in algebra how to solve this because you cannot factor it and you cannot take the square root of both sides to neatly reveal the variable because the variable's in 2 locations with different powers. So what we're going to do is learn a technique that can take any equation like this. It doesn't have to be this one. It can be any polynomial, any quadratic, and change it to look like a perfect square quadratic, which means I can just take the square root of both sides. That is really important. The third time, I will take any quadratic polynomial and convert it to a perfect square quadratic. And that's why we learned that topic first, because we're going to use it here. So there's a little technique to it. There's a few steps to it. And instead of writing all the steps down, we're going to go through 2 examples really carefully. And I'm not going to write a lot of words, but I'm going to do a lot of talking. But it's really important for you to follow every step and get to the end. And even at the end of it, you might think, well, how do I know it works for everything? How do I know it always works? Well, that's not your job. The mathematicians have proven that completing the square will always work. So you can solve any quadratic using completing the square. It's up to you to be able to follow the recipe, so to speak. So what we want to do is want to solve this equation, which is not factorable. Let's say it's x squared minus 6x minus 3, and that's equal to 0. Well, the very first thing you want to try to do, anytime you're given one of these out of the blue, is try to factor it. Always try that first. So we're going to do this and set it equal to 0. So we have an x squared, so we'll put an x and an x here. And then we look and we have a 3. So we can only do 1 times 3. That's the only way you can make 3. So you pretty much have to choose a 1 and a 3 here. And you try to pick plus, minus, minus, plus, and there's no way to do it because you can have a 1x in the middle and a 3x from the outside. There's no way to add or subtract those to get negative 6x. So this is not factorable. So not factorable. So before this, you would just give up. You would have no idea how to solve it. But completing the square is going to allow us to start with this and end up with a perfect square quadratic that we do know how to solve. And it's a 5-step process. But actually, it's only 3 steps. The last couple of steps is just solving the perfect square quadratic that comes out of it. So actually, completing the square is only 3 steps. But for some reason, it trips up a lot of students. So what we're going to do is take it slow and make sure you understand it. Step number 1. What we want to do, we have this quadratic equal to 0. What you want to do is take whatever constant number, in this case we have -3. You want to take whatever is constant and you want to move it to the other side of the equal sign. So you want to add 3 to both sides. You want to just get rid of whatever constant. So when I say add 3 to both sides, I'm not saying that you always add 3 for every equation. I'm saying you add whatever constant you have at the end of the equation, you just move it to the other side. If it were a +4, you would be subtracting 4 from both sides. All you want to do is take that constant and move it to the other side using addition and subtraction. In this case, we're going to be adding 3 to both sides. So the result of that is the following thing. X squared minus 6x is equal to 3. All we did was add 3 here, makes it go away. Add 3 here, pops a 3 over there. So you all know how to add. Step number 1 is really easy. The only one that gives people problems is step 2 because it sounds really complicated. All right, so what you need to do, you know what, in order to do step 2, what I want to do is I want to rewrite this. Actually, let's see here. First, I'm going to just go and I'm going to mark it down from what I have above. So what you want to do is you want to take this guy. You look at the coefficient that's in front of the x term. In this case, it's a -6. And what you want to do is divide it by 2. So -6 divided by 2. All you do is you take what's here and you divide it by 2. Notice I had a negative here because it's a negative in my original equation. You divide it by 2, and then you take whatever you have and you square it, right? You'll understand as we get to the end of it. So what you're going to do is you're going to look at what you got from step 1, divide it by 2, and square it. And then you're going to add this to both sides. Now, it turns out in this case that -6/2 is very easy. So this actually comes out to be what? -3 quantity squared. -3 times -3 is actually +9. So we're not actually going to add this fraction. What we do is we calculate it, we get a 9. So we add 9 to both sides, right? So then what we get is to the answer or to the solution of step 2 or the end of step 2 is we take what we had at the previous step, x squared minus 6x, and we add 9 to the left and add 9 to the right. We had a 3, so we add 9 to both sides. Notice that we haven't changed the equation because remember, you can add or subtract anything you want to both sides of an equation. I'm just choosing to add a 9 because it's been proven that when you do that, you make this equation really easy to solve. If you always take this guy, divide it by 2, and square it, and if you add that to both sides, the whole thing becomes easy. And we'll see how in a second. So what we have is x squared minus 6x plus 9 is equal to 12. Now, how did we make this easier? Because in the original problem, we did not know how to factor this. It wasn't factorable. But now I'm telling you that after you complete the square, this thing on the left-hand side is always factorable. We always can factor it because of what you've done in this process. So let's try it. So here you go, step number 3, factor. So what you do is you go ahead and open up your parentheses like you always do, and it's equal to 12 because that's what's here. And then we have x times x, and then here you have 9, and the way to factor this is to say 3 times 3, and you have to choose the signs correctly. It has to be negative times negative. Now make sure you understand that this is actually the factored form of this. X times x is x squared. Negative 3 times negative 3 is positive 9. This gives you negative 3x. This gives you negative 3x, which gives you negative 6x. Now, that's the factored form. But it's actually a simpler factored form to just say the following. X minus 3 times itself is just x minus 3 squared is equal to 12. Now, this should look familiar to you because we said we know how to solve these things called perfect square quadratics. We did a whole 2 lessons on it previously. If I give you an equation like this, we said it was a perfect square quadratic because I could just take the square root of the left and the right and it would basically reveal the variables and make it very easy to solve in one step. So now what we've done is we've come and started from an ugly expression that we don't know how to factor. We've done all this stuff and now we have a perfect square quadratic, which we can always solve. We just take the square root of both sides. So let's go off to the next board and I'm going to write that perfect square quadratic down one more time. It's going to be x minus 3 quantity squared is 12. So now we just take the square root of both sides. So On the left, we take the square root. It'll be x minus 3 left over. On the right, it's going to be plus or minus the square root of 12. And you go over here and double check yourself. That's going to be 2 times 6. This is going to be 2 times 3. Here's your pair right here. And so what you have is x minus 3 equals plus or minus the 2 comes out, and the square root of 3, which is left over, remains. And now to solve for x, you move 3 over. X is equal to 3 plus or minus 2 times the square root of 3. This is the final answer. 3 plus or minus 2 times the square root of 3. And you can write that as 3 plus 2 times the square root of 3 and 3 minus 2 times the square root of 3. You have two solutions. They're both real, which means if we were to graph the original quadratic that we had, we know that that graph is going to cross either as a smiley face dipping below the x-axis, crossing in those two locations, or going upside down, crossing in those two locations. But we know that it crosses somewhere because we've figured out what those crossing points are. So what I want to do is go over it one more time, and then we're going to do one more problem, and then over the next 4 lessons, we're going to do tons more to give you more practice with it. But the bottom line is, the punchline is, we know how to solve quadratic equations by factoring. If we can factor, we always do that. But some equations we don't know how to factor, so we don't know what to do. But we also know that we can solve these perfect square quadratics. So this process takes any quadratic and turns it into a perfect square quadratic. The very first step is you take whatever constant term you have and you move it to the other side. I actually didn't write one other step down here as well. It should be kind of in between step 1 and step 2. I'm going to call it step 1a. And I'm going to say that the coefficient of the highest power here, of this guy right here, it needs to be at 1. So the coefficient of x squared term needs to be positive 1, only a 1. So for instance, if this guy were 2x squared and so on, I would do everything the same, but I would have one other step in the middle where I'd have to divide left and right by 2 just to get this guy to be a 1. So there's really an extra step in there. I'm sorry I didn't write it down initially, but basically the very first step is you have to add 3, or add to get your constant to the other side. The next step is double check and see if the coefficient of this is 1. In this case it is, so we didn't have to do anything. If it's not 1, then you have to divide both sides by whatever's in front to get rid of it. Then the next step is you take a look at what's in the middle, in front of x, you divide it by 2, you square it, you figure out what that is, you add it to both sides. That's what we did here. And when you do that, you will always be able to factor this. And furthermore, you will always be able to factor it where it'll be exactly identical twins here in the binomials. So you will always be able to write it as perfect square quadratic. And then the rest of it was just solving that, which we've done many times before. So we want to go to the last board and do one more to make sure you understand. And then, as I said, we're going to have a ton of other examples to increase the complexity. So let's solve this guy. The equation we want to solve is x squared minus 2x minus 5 equals 0. And the first thing, of course, you want to do is try to factor it. So let's go off to the side here and see if we can. We'll try to factor it. The x squared means we're going to have x and x. The only way I can get 5 is 1 times 5. So I can do pluses, or I can do minuses, or I can do any combination, but there's no way I can get a 2, because 5 minus 1, there's no way it's going to ever give me a 2. So it's not factorable. So we're going to try to solve it by completing the square. So the very first step in this process is to take whatever constant term, in this case it's a minus 5, and want to move it to the other side. So it's going to be x squared minus 2x equals positive 5. We add 5 to the left, add 5 to the right, that's step 1. Okay. Step number 2, which I have the steps numbered differently over there, we want to check that the coefficient of x squared is equal to 1, and it is. It's already a 1 here, so I don't have to do anything. If this were 3x squared, then this would be a 3x squared minus 2x equals 5. Then I would have to divide the left and the right by 3, and that would get rid of the 3 in front of the x squared, making it a 1, and then I would proceed. We're going to have problems like that very soon. The next step is we have to do and take a look at what's in front of this guy. So we take a look at what's in front of the x term. In this case, it's negative 2. So we're going to add. We're going to take the negative 2, we divide it by 2, and we square it. Whatever is in front of here, you divide it by 2, and then you square it, which is going to be equal to, that's negative 2 divided by 2, it's negative 1. We're going to square that. What is negative 1 squared? It's positive 1 to both sides. So whatever this comes out to be, when you divide by 2 and square it, you add that to both sides. So in order to do that, we're going to add it here. It'll be x squared minus 2x plus 1 equals 5 plus 1. And you all know that that's 6, so we have x squared minus 2x plus 1 equals 6. And the claim is that once you do that, this is always factorable, and it's always going to be a perfect square. If you cannot factor this, then you've done something wrong. So then we factor. And what we're going to get here, we're going to try to factor it. It should be equal to 6. So we have now x times x. The only way I can get a 1 is 1 times 1. And the only way I can get that negative 2 in there is with a negative and a negative. Then I have a negative x and a negative x adding to give me negative 2x. These multiply to give me a positive 1. These multiply to give me the x squared. And so now I can see they're identical twins. That's what I should always get. So it's going to be x minus 1 quantity squared is equal to 6. Now this is a perfect square quadratic. We just learned how to solve those. So we're going to solve. And so what we're going to get is take the square root of the left. The square root of the left is going to reveal x minus 1 by itself, plus or minus the square root of 6 on the right. But I know that we cannot simplify the square root of 6 any further, because all I can do is 2 times 3, and I can't find any pairs. So then you just move the 1 over, making it positive 1 plus or minus square root of 6. So that means I have 2 answers, 1 plus the square root of 6 and 1 minus the square root of 6. I got real answers, which means this original equation does cross the x-axis some sort of way. It doesn't hover above or below. And I use completing the square to figure it out. So the punchline is something that I really want to emphasize because it's not something I learned when I first learned this. The reason we learned completing the square is because up until now, you've only been able to factor quadratics to solve them. Or if they were very special perfect squares, you could solve them by taking the square root of both sides. This process allows you to take any quadratic, anything I give you, and you can factor it in a way that allows you to solve it. Even if there's fractions or if there's decimals or other things going on, if you follow this process, you will be able to factor it and you will be able to solve it. And it is so powerful that completing the square is the way I'm going to actually derive the quadratic formula, which we're all going to use the quadratic formula going on throughout algebra to solve these things as well. But it comes from completing the square. So follow me on to the next few lessons. We're going to increase the complexity following this procedure. And then once you're comfortable with it, we'll move on to the quadratic formula to solve quadratic equations in algebra.